Large language models, LLMs, have become an integral part of our daily lives, powering everything from chatbots to creative writing tools. But have you ever wondered what goes on under the hood? In this video, we'll take you on a journey to build an LLM from scratch using PyTorch. No shortcuts, no libraries, just pure understanding. We'll break down the transformer architecture, the backbone of modern LLMs, and show you how each piece fits together. Whether you're a developer, a student, or just curious about AI, you'll gain a hands-on perspective on how these powerful models are created and trained. Let's get started and demystify the magic behind today's AI. The story of LLMs begins with the groundbreaking 2017 paper, "Attention is All You Need." This introduced the transformer architecture, which quickly became the foundation for models like GPT-1 and beyond. Over the years, transformers have evolved, gaining multimodal abilities and advanced reasoning skills. Yet, at their core, they still rely on the same principles. Today, thanks to open-source models and accessible APIs, anyone can experiment with LLMs. But to truly understand their power, we need to look beneath the surface and see how these models process and generate language. Before an LLM can process language, it needs to break text into manageable pieces called tokens. Tokenization can happen at different levels: words, subwords, or even individual characters. For example, the phrase "hold my math" could be split into whole words, smaller subword units, or single letters, depending on the tokenizer. This step is crucial because it determines how the model understands and generates text. Each token is mapped to a unique index, forming the basis for all further processing. Tokenization is the first step in turning raw language into something a neural network can work with. At its core, an LLM is a next token predictor. Given a sequence of tokens, the model learns to predict what comes next. This process happens one token at a time, with the model sliding its input window forward after each prediction. For long outputs, this step repeats until a special end of sequence token is reached or a length limit is hit. This mechanism is the secret behind the fluent, coherent text you see from modern LLMs. By mastering next token prediction, the model can generate anything from stories to code, all by building on what it's already written. After pre-training, LLMs are fine-tuned to follow instructions, making them useful for real-world tasks. This process, called instruction tuning, involves training the model on examples where it learns to respond to specific prompts. Without this step, the model would simply generate generic text. Instruction tuning aligns the model's outputs with human expectations, enabling it to answer questions, follow commands, or even mimic a particular style. This is how LLMs become interactive and helpful, rather than just being text generators. How do LLMs decide what to generate next? The answer lies in the attention mechanism. Unlike older models that only considered the most recent token, attention allows the model to look at the entire context. For example, in translation, the model learns that word order can change between languages. Attention computes how much each token should influence the prediction, capturing long-range dependencies and context. This is what makes transformers so powerful. They can understand relationships across an entire sentence or even a paragraph. Before transformers, recurrent neural networks, RNNs, and long short-term memory, LSTM, networks were the standard for sequence modeling. RNNs process text one word at a time, passing a hidden state forward. LSTMs improved on this by using gates to control information flow, allowing them to remember longer sequences. However, both struggled with very long dependencies. The attention mechanism solved this by connecting every word to every other word, enabling parallel processing and efficient learning of long-range relationships. Let's break down the attention mechanism. Each token in a sentence is represented by three vectors: query, key, and value. The query vector asks, "What am I looking for?" The key vector answers, "What information do I offer?" The value vector carries the actual information. The model calculates attention scores by comparing queries and keys, then uses these scores to weigh the values. The result is a context vector that summarizes relevant information for each token. This process is repeated for every token, allowing the model to focus on the most important parts of the input. To ensure the model only uses past information when predicting the next token, We use causal attention. This means masking out future tokens during training, so the model can't cheat by looking ahead. The attention matrix is adjusted so that each row sums to 1, representing probabilities. This technique is essential for generating text that flows logically, one token at a time. Causal attention is a key feature that distinguishes language models from other types of neural networks. A transformer is built from encoder and decoder blocks, each containing embeddings, positional encodings, self-attention, multi-head attention, and feed-forward layers. The process starts by tokenizing the input, converting tokens to embeddings, and adding positional information. Self-attention lets each token relate to every other token, while multi-head attention allows the model to view relationships from multiple perspectives. Feed-forward networks transform the combined information into richer features. By stacking these layers, the model learns complex representations of language. Embeddings transform raw tokens into dense vectors that capture semantic meaning. For example, words like king and queen end up close together in embedding space. Positional encoding adds information about the order of tokens, since transformers process all tokens in parallel. This is often done using mathematical patterns like sine and cosine functions. The embedding and positional encoding matrices are summed, giving the model both the meaning and the position of each token. This combination is the foundation for all further processing in the transformer. The self-attention module is where tokens gossip about each other. Each token's embedding is transformed into query, key, and value vectors. The model calculates attention scores for every pair of tokens, normalizes them, and uses these scores to blend information from all tokens. Dropout is applied to stabilize training, randomly masking some attention weights. This process allows the model to focus on the most relevant parts of the input, dynamically adjusting its attention as it learns. To capture complex relationships, transformers use multi-head attention. Instead of a single attention mechanism, multiple heads run in parallel, each focusing on different aspects of the input. The outputs from all heads are concatenated, giving the model a richer understanding of the data. This allows the model to learn patterns that might be missed by a single attention head, making it more powerful and flexible. After attention, each token embedding passes through a feed-forward network, usually 2 linear layers with a non-linear activation in between. Residual connections add the original input back to the output, helping the model train more effectively and avoid vanishing gradients. Layer normalization ensures stable activations, making deep stacking of layers possible. These design choices are crucial for building deep, powerful models that can learn complex language patterns. With the architecture in place, it's time to train your model. Pre-training teaches the LLM basic language skills using large datasets. Data preparation involves cleaning and tokenizing text, then splitting it into input and target sequences. Training uses cross-entropy loss, Atom W optimizer, and techniques like gradient clipping and learning rate scheduling for stability. Once pre-trained, the model can be fine-tuned on specialized datasets like Coldplay lyrics to adapt its style or capabilities. This two-step process is how modern LLMs become both knowledgeable and adaptable. Congratulations! You've seen how to build a transformer-based LLM from scratch using PyTorch. From tokenization to attention, from training to fine-tuning, you now understand the key components that power today's most advanced language models. While this is just the beginning, the concepts you've learned form the foundation for exploring even more advanced architectures and applications. The world of AI is evolving rapidly, and with this knowledge, you're ready to dive deeper and build your own innovations. Stay curious and keep building.